In this video, we will see how to identify the terminals of a diode, ICs and resistors. So this is essentially to make you familiar with various components. To start with, we will take up color coding of resistors. The color coding of resistors is very important in order to get the resistors from the lab or from the table. You may be using these resistors for almost all the experiments in the basic electrical and electronics engineering lab. It starts with the bands which are shown over here. They are named as color bands. Each color has got a value which is indicated over here. For instance, black has a value of 0, brown has 1, and then it goes on like that. You will be seeing 1, 2, 3 bands, plus the last band is called as the tolerance band. So it is a 4-band resistor. Now the way to identify the value of the resistor is, we take the first digit, we write the value based on the color, and then the second digit we again associate a number with the second band. Third band will be the multiplying factor. Lastly, the tolerance issue. Tolerance, of course, we are not bothered because it's for academic purpose, just to verify certain things. So tolerance may not be much important for you at this stage. Now let us take a few examples. I have given 3 resistors here. We'll try to find out the value of each resistor, one resistor at a time. So firstly, I'll take up the resistor which is given on top. Now the color of the first band is yellow. Yellow corresponds to digit 4. So I write 4. Second band is violet. The number which is corresponding to the color violet is 7. So it is 4, 7. 2 digits I have written. Third digit is black, which corresponds to a multiplier of 1. So it will be 47 into 1 ohm. This corresponds to the multiplication factor, which means the first resistor given over here is a 47 ohm resistor. This is the way we find the value of a resistor using color codes. Second example, first band we have brown, which is corresponding to a value of 1. Next we have black, which corresponds to a digit value of 0. 2 digits we have written. Third one is the multiplying factor, multiplication factor. So third is red color, which corresponds to a multiplier of 100. So it will be 10 into 100 ohms, which is 1000 ohms, or the familiar value is 1 kilo ohm. This is the second resistor. Third example, all colors are actually red. So if you all bands are red, all colors are red, even that is correct. So you try to write the value of each band. Red corresponds to 2, first digit is 2, second digit is also 2, third digit corresponds to a multiplier of 100 again. So you will have 2200, which will be 2.2 kilo ohm. So this is the way we find the resistance value using color codes. Of course, power rating is also there, but in lab, in the basic electrical lab which you will be encountering, you always use quarter watt resistor. There are resistors of the same value, same ohmic value, with higher power rating as well. The leads will be thicker. You have the terminals, so the leads, they are going to be thicker. But in lab, you will encounter only quarter watt resistors. Another point is, how do you hold the resistor? Make sure that you hold the resistor with the tolerance band towards your right, or when you hold it vertically, make sure that the tolerance band is at the bottom, so that you are able to identify the colors without making mistakes. So this is the first identification which would be required, identification of resistors. The second one is going to be the terminal identification of diodes. There are two images shown over here. They are called as p-n junction diodes. You have two terminals. They are called as cathode and anode. You have to identify cathode and anode so that you can use the semiconductor device, the p-n junction diode, in forward bias mode or in reverse bias mode. For that, cathode always is indicated by a ring. You can see a silver color ring over here. So this terminal will always be cathode. You associate a minus sign to that generally. The other terminal obviously will be the anode terminal, which is going to be positive. This is how we identify a p-n junction diode. Same thing is true for the other image also. Cathode here, anode at the bottom over here, the other terminal. This is how we identify a p-n junction diode. There is another category of diode. This is called as a zener diode, which is used as voltage regulators. Those things you will come across in the application of zener diodes, or there is an experiment in which you will obtain the characteristics of zener diode and p-n junction diode. Once again, the ring portion, of course, a zener diode is going to be a little bit translucent or transparent. It will be red color, it will be glossy, there will be a red color glass sort of an appearance. One end of that red color structure is going to be blackened, or that is where the ring is going to be present. So that ring will correspond to the cathode terminal. The other terminal obviously is the anode terminal. That is how you identify the terminals of a zener diode. Another category of diode is the light emitting diode, or abbreviated as LEDs, light emitting diodes. If you go to a shop and get an LED, get any color of LED. If it's a fresh LED, you will have longer lead. A longer lead will correspond to anode. But if the LED is going to become a bit old, or if somebody has cut the leads, then it becomes a bit difficult to identify the terminal. So in that case, the identification is done using the flat portion. The flat side will correspond to cathode. The opposite side will correspond to the anode terminal. That is how we identify the terminals of a LED. All LED colors will have a flat side. I'll indicate them here. This one, this is again the flat side over here, and the red color one. So flat side will correspond to cathode terminal. So that is the way you identify the cathode terminal. Once you identify one terminal, the other one will obviously be an anode terminal. Depending on the excitation, depending on the forward bias or reverse bias, you can excite it using a positive power supply or a negative power supply. So that's the second part, second component identification. Third one is the logic gate integrated circuits, abbreviated as ICs, wherein you identify the logic gate using a number. For instance, IC 7404 is given here. So this corresponds to NOT gate, NOT, NOT gate, because it gives the opposite of the logic input, or the inverted output. This is sometimes called as an inverter, but I generally don't prefer this term for the simple fact that you have another device, another circuit called as an inverter. So just to make things clear, I will use this term NOT gate. Now there are 6 gates available in one integrated circuit. So IC 7404, the photograph of IC 7404 is shown over here. The identification is like this. There will be a cut portion. You hold the IC in such a way that the cut portion is towards the left. The first terminal at the bottom. If you don't see a cut, there will be a dot. So that dot corresponds to terminal number 1, and then you start numbering the terminals 1, 2, 3, 4, etc. All the logic gates that you come across in lab, they are going to be 14-pin ICs. Therefore, 7 pins will be arranged in 2 rows. It's called as a dual inline package, DIP package. It's a 14-pin IC. So you will have 7 terminals in one side, other 7 terminals in the other side. So the dotted end, or the portion that is the terminal that is below the cut portion, is terminal number 1, 2, 3, etc. 7 over here, and 8 just opposite to that, 8, 9, 10, 11, finally 14. This is how you identify the terminals of a 14-pin IC. Each terminal will correspond to some function that is written over here. For pin number 14, you apply a plus 5 volt DC input. Ground is going to be the reference, so minus 5 volt, or you will have a DC supply 2 wires, plus VDC or plus 5 volt should be given to 14, minus of that same power supply should be given to terminal number 7. Then you can start using the ICs, using the NOT gates. There are 6 gates inside one IC7404, where 1 is going to be input, 2 will be output, 3 input, 4 will be the output of second IC, so on and so forth. All these 6 ICs, 6 gates can operate independent of one another. That means in case you want to use only 2 NOT gates, you can use any 2 into 2, any 4 pins, and then leave the rest just untouched. That's not going to be an issue. In case you want only 1, that is also fine. In case you want 6, even that is fine. So at a time 6 ICs can operate independent of one another. Be very clear when you use in lab, the ICs, they cannot withstand more than 5 volts. So the plus VDC should just be 5 volts. It's a DC supply plus 5 volt. Again ground, you have to connect it to minus VDC. So this 5 volt alone, you be very careful. Don't go beyond that 5 volt. This is how we identify the pins of the IC, the logic gate. Of course, we have come across NOT gate. There are other gates also. We will see the pin configuration of other gates. Now, NOT gate has got only one input, one output, so only 2 pins were used. Whereas if we take other gates, the one on the left, 7408, this IC is AND, A-N-D. I'm sure you would know the symbol of an AND gate. So you have 2 inputs and 1 output, and there are 4 such AND gates in one IC. So this is often called as a quad IC, because there are 4 AND gates inside one IC7408. Previously we had come across 6 NOT gates, whereas this will give us 4 AND gates, 7408. 7432 is the OR gate. Again, we have 2 inputs, 1 output. Pin identification is exactly similar to the previous one. We hold the IC such that the cut portion, or the one with the dot, is below, and then left hand side terminal will be 1, progresses from there, 1, 2, 3, 4, etc. up to 7. 8 will be just opposite to 7, and then 14 will be at the top left. That is the pin diagram. And these are the functionalities of each pins. 1, 2 will correspond to input, 3 will be the output, 4, 5 will be the input of the second IC, be it AND gate or not IC, gate, second OR gate or second AND gate. Now generally the notation is A corresponds to input. So if we want to represent or use one gate, we will write it as 1A, 1B, which means A and B, they are the inputs. Output is generally called as Y, denoted by the letter Y. So 1A, 1B will be the input, 1Y will be the output. Similarly, second input will be 2A, 2B, third will be 2Y. Third meaning the third terminal of the second gate. The individual gate numbers are indicated over here, 1, 2, 3, 4, as you can see very clearly. So there are 4 gates inbuilt. This is called as a quad IC. So we have come across NOT, NOT gate, and then AND gate A and D, AND gate 7408, 7432 is the OR gate, and then we have the inverted version of the AND gate, which is NAND, N-A-N-D. IC is 7400. Again, same configuration, 1A, 1B, 1Y. 1A, 1B, 1Y will be the two inputs, one output of first NAND gate. Goes on like that. Again, VCC should be connected to plus 5 volt. Ground should be connected to minus VDC or minus negative of that power supply or 0, so on and so forth. It remains the same. That principle remains the same. And the next gate is the inverted version of the OR gate, which is NOR, NOR gate, negative of gate or inverted of gate. 7402 is the IC number. This alone you need to be careful, because the pin configuration is output will be the first terminal, whereas the other two things will be the inputs. 1A, 1B will be the input to the NOR gate. 1Y will be the output, which will be the first terminal, first pin of the IC 7402. Similarly, fourth pin will be the second output. I will indicate this as 2Y, and then I'll have 2A, 2B. As always, seventh pin will be ground. These things don't change. 14th pin will be VCC. Those things will never change. Whereas the input and output alone, you may have to be very careful. Whereas this will be 4Y, 4B, 4A. I hope you understand this. 4A is input, 4B is input, 4Y is the output. 3A I am not indicating. This is 7402. This alone you have to be very careful. Generally, as an added information, you take the data sheet of the IC, any particular IC, in case you want to know the pin arrangement of 7400, 7432, 7402, etc. Take the data sheet, just Google IC 7402 data sheet, you will get a PDF version. There the pin details and the pin arrangement will be given. So that is just an additional information, because sometimes some manufacturers, they may arrange 7402 in a different way. Just for clarity purpose, I am telling this. You can take a data sheet and refer to that in case you have any confusion. So to summarize, the various gates that we have come across, the IC numbers are presented over here, first column, whereas the gate function is presented in the second column. 7400 corresponds to NAND IC, NAND gate. IC 7402 corresponds to NOR gate, 04 corresponds to NOT. 7408 again, and 7432 corresponds to OR gate. There are other functions as well, XOR gate, those things I am not handling, because you may have to deal only with these 5 basic gate logics. So that is enough. So remember the IC number and the particular gate logic which they correspond to. It starts from 7400 NAND, 02 NOR, 04 NOT, 3 negatives, 3 inverted operations start from 7400, 02, 04. And then comes the normal operation, AND gate and OR gate. 7408 is AND operation, 7432 is OR operation. With that, I'll wind up this lecture.